We were discussing powder bed fusion systems, and we were mainly focusing on selective laser sintering. And we discussed some sintering processes, some different types of sintering, like solid state, liquid state sintering processes. And now we will focus on some powder handling issues, how we distribute the powder on the bed, and how we try to satisfy uniform thickness for the new layer. We'll be focusing on such issues and then discuss some other details related to powder bed fusion processes. So if you remember our initial schematic on this powder bed fusion systems, we have a system here called as counter-rotating powder leveling roller. And that's a very popular one, and it was patented, so that's why some other companies try to come up with new solutions. And if you remember my video, EOS company had a different one. They had hoppers, and some powders were actually poured on the, let's say, carriage in their system, and then carriage was actually pouring, spreading the powder on the table. But they were not using this counter-rotating roller due to these patent issues. And what are the requirements from these powder delivery systems? First of all, you need to have a reservoir, a kind of a powder tank, which has sufficient volume for. So can anyone tell me the requirement for that? Any relation between the volumes? So if you have 2 feet cartridges here and you have built platform, so what is the relation between the volume of these regions, these parts?
If we add the 3 cartridges together, it should be equal to the powder bed, I think.
Yep, that's the main thing actually. If you have, let's say, a volume of powder bed, then you need to have a volume of material volume in these cartridges. If you have 2 of them, you may have half of it here, half of it on the right hand side. So this is the main simple requirement for the reservoir. Since in the biggest challenge, in the maximum case, your part may fill the complete, let's say, building bed. Another requirement about delivery systems is the correct amount of powder on the layers. This is highly important since if you have incorrect powder, incorrect amount of powder on the layer, then your laser will not be able to do the sintering. Where is my, okay. For instance, you have such a case and have, so if your powder is here, around here too much, then your laser may not be able to melt all these or sinter these powders. So this thickness, this amount of powder on the layer is highly important. And another issue, you shouldn't have obviously less powder. If you have less powder on it, then what is going to happen? So you may actually, if you have less powder, then you may melt even 2 layers underneath, so which is not actually accepted. So your powder handling system, your roller or blade should be able to spread the correct amount of powder on the bed. Another issue, it should be as smooth as possible, and usually it should be thin, and it's mostly less than, let's say, 0.2 millimeters. But there are companies which are trying or working on some 50 micrometer layers, even there are, I think, 30 micrometer layers. But obviously, they are using very small powders, having a very little diameters, and it's quite challenging. Another issue is that you should have all these in a repeatable manner, do all these tasks in a repeatable manner. You shouldn't have a thicker one, a thinner one. Their thicknesses should always be the same. Another important issue is the shear forces. You shouldn't apply shear force on the previous layer. while this one is actually moving to the right. It shouldn't apply any shear forces to the previous layers. What happens otherwise? You will deform the previous layer and the quality of your part will be decreased. Even you may break the part depending on the amount of shear force you are applying. So these are the main requirements we should have in the delivery systems. Any questions, guys, on this issue?
Hocam powder reservoir of sufficient volume ben tam olarak anlamadım da bir daha anlatabilir misiniz acaba?
The first one?
Evet.
Okay, let's say that this is a build platform. As you know, this one is going down once you sinter a layer, and then it goes down a little bit, one down, and it has such an actually volume. It's a kind of a box shape. Initially, you have just a single layer, and then depending on the number of layers required in your fabrication process, it will have, let's say, n number of layers. But in maximum, this will have a value, let's say, m max. And this m max value will result in some, let's say, volume, and assume that this is V, the maximum volume you can have in your printing bed. And in order to do that, you need to have, let's say, V amount of actually powders available in your cartridges. So if you have 2 of them, at least you should have more than V over 2. And again, it's the same for the right hand side. It should be more than the half of the volume we have in the powder bed. What happens if you have less than? Then probably to the when you are around the top layers, you will not have enough powder here, and your powder, let's say, spreading system will not be able to spread uniform powder on your bed. So this is an important issue, and since most of the times we will have extra materials, extra powders here, that's why we should have more than, at least more than the half of the volume of your bed. Any other questions, guys? There's a question on
Dördüncüyü
chat.
tekrar edebilir misiniz?
Which one?
No shear forces on the previous layer dediğinizin
Okay.
sebebini.
Let me draw a kind of a shape here. Assume that this is a sintered layer. Let's draw some solid parts here. These regions are sintered. Okay, assume that this is the sintered region, and now we are spreading a new layer of powder. Okay. Now our laser will move on this and do sintering, but while you are spreading, while your counter-rotating roller is rotating and also at the same time moving to the right, it may damage the previous layer. And we will later see that there is also a system called as ductor blades. We have a kind of a blade here, and this blade is moving to the right or left, depending on the location of this blade. It may do harm on the previous layer. So once it's moving over this sintered region, it may harm these particles which are already fused together. So if that happens, obviously you will deform the previous layer, and probably you will have some quality issues once the product is fabricated. Is it okay, Kilian?
Yes, I understand. Thank you.
Okay. One more question on the chat. Could we be able to change the layer thickness for different sections of the drawing? You may do it, but most of the printers, most of the companies actually do not let user change these parameters during the print. The thing is that once, if you have, let's say, a thin layer first and a thicker one, then your laser power should be enough to actually sinter the complete layer. If you have such a high power laser, yes, then it's doable. But as I mentioned, due to the quality, due to stability problems, most of these companies, manufacturing companies, actually do not let users to play with these layer thicknesses or other laser power issues. Any other questions, guys? Okay, let's clear this part. Oops, sorry. Yes, what are the challenges? And we have some challenges. Obviously, this is another easy task. You need to be careful while spreading these powders uniformly, and your system should be satisfying these requirements. And also, some universal characteristics of the powder feeding system should also be considered. For instance, if you have smaller particles, as the size of your particle decreases, let's say, think about fluor, okay? If you have smaller particles, then you'll have more friction or more interparticle friction between the powders, and there will be more electrostatic forces, and these will result in a decrease in the flowability. So we have an advantage of smaller powders, since if you use smaller powders, then that means your accuracy, your resolutions will be much better. You can fabricate highly detailed products. But the thing is that while spreading the powder, you may have problems, since the flowability of smaller size particles are very low, and this is due to the fact that we have more friction between them and more electrostatic forces. So that's why we need to find an optimum value for the particle size and try to avoid such problems. So in summary, you need to have flowable powders. Another thing is that if you have, let's say, surface area, have more surface area according to the volume. If this ratio is high, then that means our surface energy will be increased, and the powders will be more reactive, which means that we may have some chemical reactions, and that might result in worse quality. So you need to take care of it. And sometimes, in order to overcome this issue, we have controlled atmosphere. We will see in upcoming slides that some especially metal-based systems use such vacuum systems. The interior of the machine is in vacuum, and we don't have any gases around, or sometimes we use inert gases. Instead of having a vacuum atmosphere, they actually pump some inert gases into the machine so that we will not have any reaction between the powders and the laser beams and the powder itself. Another issue, again, your system should be capable of minimizing the airborne particles. We shouldn't have any particles moving around, so you should clearly be spreading the powder without any moving any powders around. That's another requirement. And lastly, obviously, as I mentioned, if you have smaller particle sizes, your surface quality will be better, your accuracy will be higher, and you will have thinner layers, which means that the staircase effect will be somehow eliminated. You cannot completely eliminate it, but at least it will be quite difficult to see on the inclined planes. So in summary, we can say that you should try to use minimum size particles while actually overcoming the negative effects of such powder systems. So this is a quite challenging problem. You should always do some kind of tests on your material and try to find the optimum size for your powder bed fusion system. Any questions, guys, on these issues, power handling challenges? So you see, with our powder handling system, we have a counter-rotating roller, we have feed cartridges. These feed cartridges are moving upwards, and they provide extra powder around. And then with the help of this counter-rotating roller, we spread them on this table uniformly. And let me draw the side view. So we try to have a uniform amount of powder on the bed all the time. And obviously, we always have some powders around this bed, right? We cannot eliminate it. We always have powders around, and sometimes you may have a kind of an, let's say, gap, and these extra powders might be stored in recycling units. And once this roller is on the right-hand side, here, it will be quite difficult for me to draw, but let's do it. Yes, once it's on the right-hand side, then this one will move up. We will have extra powder, and then by simply moving our counter-rotating roller to the left-hand side, again, we will spread the powder. So this is for actually decreasing the fabrication time. You may have a single one, but that will be a time-consuming case. By having 2 cartridges or 2 hoppers, we can save time while printing the part. So while these cartridges are moving up, obviously our platform should go down by 1 layer, and this powder, this push powder is, as I said, will be spread by the roller, and this counter-rotating roller is actually counter-rotating motion is a very nice issue. By having this, we can obtain quite uniform, let's say, layers. And another advantage of it, we will have less shear forces. It's a cylindrical part. It's rotating around itself in the counterclockwise direction, and it always decreases the shear forces. You will in a moment see that other types of powder handling systems will have more shear forces on the previous layers. Now I will show you an example here. I actually recorded this one in Izmir in a company which is working on kind of a selective laser melting system. And they have a kind of an inert atmosphere inside, since they are using metal powders. This part is this left-hand side is the cartridges. This one is moving up, and this is build platform, and this is moving downwards. The size is not much. As far as I remember, it should be around 5 centimeters. The diameter of this circle cylindrical shape is 5 centimeters. Let's see it. As you see, this they are using a ductile blade kind of thing for powder handling. They are not using a roller or a counter-rotating roller. And this one moves a little bit, and then the blade actually takes all these powders and spreads them on this region. Whoop. Now, as you see, we don't have any melted particles. Now the laser will work and try to join these powders together. Do you see the laser? I think here it's not that difficult. Yep. Now one layer is actually formed, and now this ductile blades will move to the left. By the way, they didn't have 2 cartridges. They just used a single one. But instead, what they do in order not to have shear forces while moving right to left, they have kind of a tilting. They were tilting the blade. Any questions, guys, about this powder handling system? Okay. So yes, this is actually the mentioned thing, the ductile blade. It's a very simple system, but quite useful. As this one is moving to right, let's say, with the help of simple hinge here, it spreads the powder on the table. And the thing is that compared to the counter-rotating roller, this has higher shear forces, but you can decrease it if you have some ultrasonical vibration around. You can do it also with such little vibrations. Their amplitudes are not much, but the frequencies are higher. We have another system, and this was actually the system utilized on the EOS machine I introduced you. These are called as hoppers, and with the help of them, they have a kind of a gauge system here, and some amount of powder is, let's say, poured on the table, on the platform, and then with the help of this blade, it spreads it uniformly on the table. And you can also use it with the counter-rotating roller. As you see, powder is poured on the platform, and then by moving this rotating roller over the platform or the table, let's say, we have a uniform layer. As you see, this has a uniform thickness, but before going over it, we have some bumpy regions, we have some kind of valleys and hills, but after going over it with the rotating roller, you'll have a uniform thickness. So obviously in this hopper feeding system, we are feeding the powder from above, and we can make use of this system with blades or with rotating rollers. And again, in order to obtain uniformity, high uniformity, and to make your powders flow, you can have some kind of ultrasonic vibrations in the hopper. Another issue about these hopper systems is that you may have multiple hoppers. One hopper might be responsible for a specific material, and the other hopper may provide you secondary material. So that might be a nice actually solution for obtaining alloys. And we have another issue regarding the powders. Since they are quite expensive, it's better we do some recycling. And another issue for the recycling is that we are performing our fabrication in a bed, right? Let's say this is our bed. And even though if you are simply, let's say, printing such a longer shape, okay? Even you are printing a simple one, a very low volume part, you need to fill this bed actually with powders. This is actually the biggest disadvantage of this powder bed systems, and that's why companies are always waiting for more parts to be printing. They do not print a single part in a single bed. Instead, they usually have many of them at the same time, and their advantage is that they can put parts on top of each other. Since we said that you don't need to have support structures, you can easily place such parts on top of each other, even though they require, let's say, support structures, since these supports around will act as a support structure. You don't need to have special ones. This is the main advantage, but the thing is that if you want to print a single part, then it's quite, it's not meaningful, since you'll waste lots of power. And the thing is that you can recycle some of it, but not completely. Since why we cannot completely recycle, since we have high temperatures always in the beds. The temperature is a bit around, let's say, 0.5 more than the melting point temperature. Once it's higher than that, then we may have some powders actually joined together. So we will not be able to obtain the same uniform, let's say, or pure sphere particles. Instead, we may have such elliptical parts or larger spheres, and that's why while you are doing recycling, you cannot completely use recycled powders in your new printing operation. Instead, we mix these recycled powders with new powders and try to obtain a kind of a uniform mixture. And with the help of it, we try to increase the strength of our parts. And additionally, not just the temperature, but the atmospheric gases may also do the same. They may cause such reactions, and these particles may be fused together. Another issue, if you have high temperatures, higher than this value, the molecular weight of the polymer will be modified, and they will not be equal. They will not have equal properties with the raw particles. So what we do, we have some ratio. For instance, in our textbook, they say that you may have 1 unit of recycled powder and 1 unit of actually powders on the, let's say, bed. Is that right? As powders in the machine, or but this is quite difficult to obtain. You may have some special equipment, vacuum systems. With the help of them, you can gather these powders around the machine. So they say that you may have 1 unit of recycled, 1 unit of powders from the machine, and 1 unit of new particles, raw particles. So if you have such a uniform mixture, they say that the quality of your part will be quite okay, and you can save some money by using these recycled powders. But in the EOS system, they were using a ratio of 3 to 7, and this was recycled powder, and they were using 7 units of new powder. Any questions, guys?
Hocam, bu şimdi işlemin gerçekleştiği ortamı ısıttığımız için aslında biraz da bu olay ortaya çıkıyor, değil mi? Yani peki biz ortamın sıcaklığını çok fazla yükseltmesek, yükü lazere versek, diyelim ki kapasitesi yeterli. Bu durumda bu oranı değiştirme imkanımız oluyor mu? Hani diyelim ki materyalden daha az harcamak istiyoruz.
Yep, you can increase. Probably you can make it, let's say, 1:1 maybe for EOS, or even you can make it 6:4. Yes, you're right, but the thing is that you need to have a high power laser. And another issue, the powder around the bed, inside the bed, might be affected. Even though, let's say, this is the top view, this is the region you are trying to sinter, and if your laser power is higher, then probably the powders around this part will also be affected a little bit. So that's why, actually, if you remember, they are using a kind of a screening system, so that they are actually removing powders having, let's say, higher diameters, larger diameters. Instead, they want to use the same diameter, even if it's recycled. Otherwise, you will have non-uniform layers, and that will actually result in big issues.
Hocam ben şeyi soracaktım. Bu recycle etmek için belirli işlemlerden geçiyor mu?
Yep. Do you remember the videos I showed you? They are first using. Let me show them once again. Yes, this is the first thing. Actually, they are using screening. It's vibrating, and the particles having larger diameters will be on the top, but the remaining ones inside, underneath this screen, will be utilized. First, these are joint, let's say, powders. You cannot use them in your printing operation. And after you have this recycled powder, then in the second step, you put all these recycled powders and new powders into this, let's say, mixing system. With the help of it, you can have a uniform mixture. This is a mixing system of powders. They mix actually the unsintered powders, unused powders with the new ones, so that the quality, the strength of the new parts will be better. They don't want to use completely recycled powders in the new products. Otherwise, it will be a bit, let's say, brittle, and probably it will have less strength. So that's why they have a kind of a mixture. Usually around 30% of the powder is from the recycled ones, but the 70% is new powder. Okay, any questions?
Hocam bu şey demiştik ya, bulunduğu ortamdaki hacimde ekstra kalan yerleri kullanamıyoruz. Yani onları yeniden geri dönüştürmemiz gerekiyor. Bu oran çok yüksekse eğer o build platformu daha böyle adjustable bir hacim mekanizması yapsak ya da değiştirilebilir olsa daha mantıklı olmaz mı?
Yes, but it's quite difficult. I was also thinking about that issue. We focused on some concepts, but we didn't come up with a feasible solution. If you can find such a solution, then we may apply for a patent. Okay. Yeah, this is a nice issue, but right now there is no solution.
Teşekkür ederim. Peki hocam oran ne kadar oluyor? Yani yaptığımız parçanın hacmi bir birimse ne kadarlık bir kaybımız oluyor genel olarak?
It depends on the size of, let's say, your powder bed. If your powder bed has a volume of, let's say, 10 units, and if your part has a 1 unit, then that means 9 amounts of powder should be recycled, and you cannot completely use them. So it's quite a high number, I can say.
Teşekkür ederim.
Welcome. Any questions, guys? Up to now, we will switch to metals. We'll discuss some issues about metals. Since the systems, these powder bed fusion systems, are not just for polymers, not for, let's say, polyamide. We can also use such systems for various types of metals, like, let's say, aluminum, copper, titanium. There are such systems, powerful systems, where they also melt or fuse such powders together. And for difficult metals, they need to use high power beams like electron beams. Laser will not be enough, so that's why they use, especially for titanium type of alloys, they prefer to use electron beams. Before going into details of metals, I want to actually state an important issue. In the polymer systems, we don't need to use support structures in between the parts. Once you put them in the bed, the powders will act as a support structure, but for the metals, they don't do it. They use some support structures. The reason is that they have high amount of actually heat, and they want this heat to be, let's say, distributed in the bed. So that's why they use support structures to distribute heat and also keep their, let's say, inclined surfaces in place. In metals, due to the high temperatures and high heat generated, they make use of such support structures and heat, let's say, dissipating structures. So this is the main difference with respect to the polymers, but the other fundamentals are the same. Again, we will have some cartridges. They, depending on their orientation, they may move up or simply pour powder on the table. And in all of these, we will always have build platform which is moving downwards. And for the metals, we may have two options. The first one is full melting. As the name implies, in the full melting, we are melting these powders. They will be in a liquid state and they will be joined together. And this is done with high power lasers and with electron beams. And you can also do it with a kind of a special way. This is called as liquid phase sintering. In this approach, what do they have is that they have, let's say, this is metal, and then on top of metal, they have a special kind of binding material. And once they increase the temperature, this binding material will be liquefied and the parts will be joined together. But the thing is that if you are using liquid phase sintering, then you need to do some more extra operations. You will do take your part and put it into a sintering oven, and then even you may need to do infiltration to fill the gaps inside your part. Otherwise, you will have very low strength. So This is easier to do in terms of just the machine, since you don't need to use high power laser or special environment. But the thing is that after this process, you need to spend more time on post-processing, like secondary sintering and infiltration. So this is actually the similar things to the previous topic I mentioned. We have some polymers actually coated around the powder. As you see, these black ones are secondary material. These are called as polymer binders, as you see here. So in the printing, you will obtain a green part. Like in the case of powder metallurgy, your fabrication will not be finalized. Then you need to do some further sintering. And this is done in a special oven, in a special furnace. And after furnace, you will have such, let's say, fusion between your original powders. But obviously, you will have high porosity levels. These are some gaps, as you see. These yellow regions are gaps. So what you can do is to simply an infiltration process. If you apply an infiltration process, then these gaps will be filled with secondary material. You may, for instance, use copper or different materials. And at the end of this infiltration, you will have a highly dense product. And actually, let me try to show you the fundamentals of this company. They were focusing first on composite type of printing, but I think for about 2 years, they also start working on some metal products. Their system is called as MetalX, and they somehow use this fundamental approach. Let me show you. Yes. Any questions, by the way? So this is their system, and let me see if they have any other information. Yes, you see after the part is printed, they need to do some washing and extra sintering. In washing, they try to remove the powders around and then do the sintering. But what happens in the sintering part is that the part shrinks a lot, usually around 25% or something. So in their software, actually, they first do kind of an larging scaling operation, and then once this secondary sintering operation is finalized, you will obtain the desired sizes. And these days they are focusing on copper. They obviously work on steel, but I think their new research is mostly on copper material. These are some example products they obtained by their system. And you can see they are also working with difficult metals like inconel, some superalloys. You can have a look at them. They also work with obviously some steels. Let me see if they have any other information. Let's have a look at their latest products, X7. I'm looking for a video, but I think they don't have. Or let's have a look at system details. Not. I may talk about their data sheet, but this is not the thing actually I was planning to mention. So let's switch to our slides. Okay, guys, do you have questions regarding this fundamentals about metal parts, fusion of metal powders?
Hocam infiltration'daki proses tam anlayamadım. Aralarına nasıl şey giriyor?
It's very similar to the powder metallurgy. You use an lower melting point, let's say metal, usually it's copper, and you are going to put this one into an oven and some amount of copper around, okay? And then you start increasing the temperature. Once the temperature is increased, then copper will be melted, and due to the capillary effect of this liquid, it will flow into these openings. And at the end of the operation, all the copper actually will be inside your part, and you will have almost zero porosity, and it will be a fully dense product. I think I have a link for a video for infiltration in the upcoming slides, so I will show it to you in a moment, I guess. I think you had another question.
Hocam ben şeyi soracağım. Liquid phase sintering'de secondary sintering ve infiltration yapılmalı dediniz ya. Bu ikisinin farkı ne? Secondary sintering ve infiltration aynı şey mi? Yoksa bu fotoda gözüküyor mu?
In the secondary sintering, you completely remove these polymer binders. You get rid of them. In the first sintering, with the help of these binders, you join these powders together. You join these gray powders together. But in this secondary part, in secondary sintering, this is actually it. You get rid of all these black material. As you see, we don't have any black here. These are polymer binders. In the secondary sintering, our main focus is on the removal of polymer binders.
Tamam, sağ olun.
Okay. Another case where you can make use of actually such powder bed fusion systems is to obtain the pattern. And now I will show you an example. They are using a powder bed fusion system to obtain the molds for casting operations, sand casting operations. So their powders will be now sent, and at the end of their process, they will obtain huge, let's say, molds, and with the help of it, you can do casting operation. Now I will show it to you in a moment, but we have an advertisement. Any questions, guys?
Metallerde soğutma işlemini nasıl yapıyorlar layer'lar üretildikten sonra?
So your question is, how do they cool the parts after the whole part is finished, or?
Yok hocam, whole part değil. Hani temperature'ı ayarlamamız gerekiyor ya diğer layer'ı da zarar vermemek için. Sanki öyle bir şey vardı. Anlık soğutmak gerekiyor. Onu nasıl yapıyorlar?
No, they don't have such a cooling system. They don't have any fans around. They just trying to keep the temperature in the beds at a fixed value. And the laser just increase the temperature of the powders in the corresponding regions, but we don't have any cooling system. We just cool the laser. Laser in the interior of the laser is cooled down, but the atmosphere, the printing regions are not cooled. They are cooled after the part is finished. Now I will show you a company called as X1, and they are producing sand molds for metal products. I'll skip the fundamentals. They obviously use a similar CAM software. I'm skipping these parts, and since they have a larger build volume, so that's why they try to print many of these molds at the same time. So this is their huge machine, huge printer, and they are only using sand. And at the end of the process, they will have sand mold. This is their sintering head. It's moving, as you see, kind of scanning the plane. If you have a look at this table, clearly you can see the sintered regions. Another layer, now they will spread some powder. Oh. This is their kind of hopper, I guess. As now it's centered. Another sintering operation. They are not obviously melting the sand particles, they are just joining them together. Now the cleaning part, they are trying to recycle the sand. As you see, they have a kind of vacuum system. This is their powder bed. Yes, now this mold is, one part of the mold is ready. It's quite brittle, so they should be careful. Now the parts are going to be cleaned with the help of such air jet. Now they are joining the mold parts together by using such glue. So this actually mold has, I think, 4 parts, which is quite difficult to obtain with conventional approaches. So that's why they used 3D printing to obtain the mold. Now they are doing the casting operation. And after it's solidified, they will simply remove it. And they will not be able to use, obviously, this mold once again. This is expandable mold. And that's why they actually printed many of them at the same time. Now you'll see that it's a quite complicated product, which is not possible to do it with single or double molds.